The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so let's get started. I'm just trying to wire myself up here. Okay, so before we get into the PowerPoint here, so basically what I'm doing is I'm picking up from the point where we left last time, where we're discussing waves, and what I would like to do now is derive a wave equation, basically a mathematical form that should allow us to predict different kinds of waves, not waves. All right. So what I start with here, I start with a general function psi of an argument eta. So for those of you who are not fluent in Greek, this is psi, and this is eta. Okay. And these are, at the moment, these don't necessarily have a physical meaning, but in order to produce a wave out of this function, what I can do is I can write it as C or F of z comma t equals C of z minus ct. Okay, now why is that a wave? If you, first of all, z now has become a spatial coordinate, t as usual is time, so if you actually hide time, so now time is 0 or time is a constant or something like that, then you actually have basically the same argument. But if you allow time to increase, then you can see that the time increase will have the effect of sliding the same shape along the spatial axis. So for example, if let's take this as our reference point here, the first peak, after you advance time a little further, then this point has moved has moved to the right. And how much is this distance? Well, anybody? This is easy. I'm just trying to see if the people in Boston have woken up. Yes? Nobody's awake in Boston. Okay. So this distance equals ct, right? Because if I set the argument of this function to 0, then basically I recover my original function. So basically, as I advance time, the effect is that this waveform moves to the right. Okay. So now what we do is, and at the moment there's no obvious motivation for why I'm going to do what I'm about to do, but please take my word for it for a while. I'm going to take two partial derivatives. I'm going to take df dz and df dt. Okay, df dz equals basically psi prime, where psi prime, I use psi prime simply to denote the derivative of psi with respect to its mysterious argument. So that's very easy. What about df dt? That's right. I have to apply the chain rule because there is a multiplicative argument inside. So this is going to be minus c times psi prime. So because psi prime appears in both places over here, I can combine these equations and say df over dz equals minus 1 over c df dt. Okay. So that is a partial differential equation, and you might say, well, what I did is a little bit stupid, right? Because I had a relatively simple expression for the wave. I actually had the wave just in front of me, and what I did is I wrote a partial differential equation, which is not very intuitive. But the benefit of doing that is, of course, that the wave that I wrote here is a very special, very limited kind of wave that propagates without changing shape, without anything fancy happening. We know from experience, for example, in real life, if you have ever seen water waves, they don't quite propagate like this. They change shape in all kinds of complicated ways. So even though I derived this equation from that simple shape, we will see a little bit later that this equation actually can describe much more general waves. We're not quite done yet, because the equation that I derived here applies for a wave moving to the right. I can equally well consider a wave that is moving to the left, and in this case what I would have to do is I would have to write f of z comma t equals c of z plus ct. A little bit of thought will convince you now that if you advance time, then the wave will have actually to move to the left, towards negative z, in order to maintain its argument. And if I do the same game now, I can I can write df dz equals psi prime. That did not change. This time df dt equals plus c psi prime. Now I have another partial differential equation, df dz equals 1 over c df dt. Okay, let me put back the equation. So this is a wave going to the left, backwards, and I had another equation, df dz equals minus 1 over c df dt, and that is a wave going to the right. Okay, you can see very easily that if you take a second derivative of these equations, you would actually, let's go back to the first one. If you do the second derivative, d square f dz square, you will pick up an extra minus sign from the same equation, and you will find that it is 1 over c square d square f dt square. You can do the same in this equation. There's no sign here to begin with, so it is 1 over c square d square f dt square. So basically this single equation can describe both forward and backward propagating waves. And this equation, actually it's a three-dimensional version, not this one, but it's a three-dimensional version. It has the name Helmholtz wave equation. And because Helmholtz is a little bit difficult to pronounce, actually that's not the reason, but the reason is that, anyway, it's a very commonly encountered wave equation. So typically we simply omit Helmholtz and we say wave equation. Now why we might want to distinguish this as opposed to, are there other wave equations? Yes, there is the Schrödinger equation, there is the Klein-Gordon equation, there is the, for those of you who do fluid mechanics, there is the Korteweg-de Vries equation, also known as KdV. There's a bunch of different wave equations, so we need some way to discriminate. Nevertheless, the other wave equations, they are referred with their names. So when you want to refer to Schrödinger's equation, you say Schrödinger's equation. By convention, when you say wave equation, you mean this one, so the Helmholtz. Okay. So this is all very nice, and it's actually done on your slides, so there's no reason to agonize over what I did over here. What I would like to remind you before I move on is for the simple case of first of all, you can imagine that this is a very general kind of solution, because what is psi? After all, I put up this strange shape over here. I didn't say where it came from. So for that matter, if someone gives you the wave equation, how can you go ahead and solve it? Well, we're not going to do this in great detail here. This is a little bit beside the scope of the class. But generally, if you need to solve a partial differential like this one, you need additional information. You need the initial conditions, how did the wave start at time equals 0, and you also need the boundary conditions. So what happens to the wave as it expands? Sometimes the boundary condition is at infinity. Maybe the wave is not bounded, it can propagate outwards all the way. And that's a good example of what happens if you are, flying with a helicopter on top of the ocean, and you drop a stone into the surface of the ocean. Then the wave that you generate, to a good approximation, you can use infinite boundary conditions, right? Because the ocean is not quite infinite, but very large. If you are generating a wave in a small channel, then you might have to include boundary conditions, right? Because the wave will be confined by the walls of the channel. And we will see later that this is actually quite commonly the case in optics. We don't call them channels, we call them waveguides. But the boundary conditions can actually significantly alter the shape of the wave. So what I did here is just so to give you an idea, I quote-unquote solved. Nothing interesting happens here, but this is actually a solution of the wave equation with a particular initial condition where at time equals 0, the wave is a sinusoid. So I basically said that this is my equation, and I say that f of z at t equals 0 equals some sinusoid with amplitude a and wave number k. If that is the case, then all by inspection, I don't have to do anything. Very important, and what I did not write down, but it is implied, is that the boundary conditions are free. So this wave is free to go as far as it pleases without any spatial constraints. So if that is the case, then you can write the solution almost by inspection. F of z comma t equals a cosine kz minus ct. And you can see by inspection here that because of the way I wrote it, this actually satisfies both the partial differential equation, the wave equation, and the boundary condition. So therefore, this is a proper solution of the wave equation. In fact, I only wrote half of it. The wave, remember, can go forward and can go backward. So to cover both cases, I actually write the solution this way. With the data that I have here, actually, I don't have enough to specify. Actually, in principle, the wave can go both ways. I would have to apply to give you additional information to know which actually happened. The other thing that I wanted to point out, which is not really difficult, but it takes some getting used to, is the various terms that appear inside this equation over here. So the term that we've been very familiar with is the wavelength. There's another of those crazy Greek symbols that's called lambda. And the wavelength is related to the quantity that we have over here as 2 pi over lambda equals k. So lambda is the wavelength, as I said. K is known as the wave number. So the relationship that they have is, if you think of the wavelength as a period, which it is, the period of the wave in the space domain, then k would actually be the angular frequency. But we call it wave number to keep them separated. Okay. Equivalently, you can define the actual angular frequency of the wave. Usually, this goes by the symbol omega. And from this equation over here, very simply, you can see that if you wanted to write it in the form A cosine kz minus omega t, then clearly omega is the angular frequency, and by comparing the two equations, you can see that omega equals kc. So the angular frequency then is related to the spatial frequency, the wave number, and the frequency and the speed of the wave. And of course, this is nothing new because we've seen this equation before, but we saw it in disguise. And that's why I'm going through this, because all the symbols, they can be played around with quite a bit. So this equation I can rewrite, and the way I write is like this. So omega is the angular frequency. I also have the plane, so to speak, frequency nu, which is related as omega over 2 pi, okay? So one of them goes a full steradians, is measured in full radians per second. This is omega, nu is measured in hertz, simply inverse seconds. Okay, bless you. So, so I can substitute in this equation, omega is 2 pi times nu, k, according to my equation over here, is 2 pi upon lambda, and c is c. So the 2 pi is cancelled here. The 2 pi's cancel here, and I end up with equation c equals lambda nu, which I think we've already seen a couple of times before. We call it the dispersion relation of the wave. Okay, so this is how all this come about. I haven't said anything new about this. I'm just trying to point out the different ways that this equation can manifest itself. Okay. And the other two terms that we encountered last time, and I wanted to remind you, one is the amplitude of the wave. This is this constant A over here. For some reason in the slide I decided to call it A naught. Anyway, it is the same thing. And also, so we said last time that in general, the wave can also have a phase delay. So in here, I can also add the constant plus phi, which does not really do anything by itself. All it does, if you wish, is equivalently, it shifts the time origin. So that's a relatively trivial thing, because after all, I am free to start my clock whenever I want. If I have a wave that never changes, I can start my clock whenever I want. So it doesn't really make a big difference. But we saw last time that if you have two waves that are, as we said, interfering, so they're simultaneously happening, so to speak, then the relative phase delay between the two can actually be quite significant. And I will play this movie again. In this case, the two waves are actually, they have the same phase between them. In other words, if you look at the center, they're both simultaneously bright or simultaneously dark, whereas in the other case, it's the other way around. They're off by pi. So when one is maximum, the other is minimum. I think it is worth playing this one. This also has the interesting effect that it can hypnotize you. So for those of you who are in Boston and are not fully awake yet, yes. Oh, so when you ask a question, you need to push the button.
So for example, now two waves travel in the opposite direction. Yep. They have same amplitude, but perfect cancel each other. So in this case, where does the energy go?
They don't quite cancel each other, right? So as we will see. I will actually do this in a second. It's called the standing wave. So you will see that they don't quite cancel. They just produce what is called the standing wave. So I will get to your question in maybe, I think it's actually coming up next. Yeah, so give me a second and I will get to your question. Okay. So there it is, a standing wave. So like your colleague asked over here, suppose that you have a superposition of two waves. Now both are solutions to the wave equation. Now by its looks, I don't want to do the proof here, it takes 3 lines, but by its looks this is a linear differential equation. So basically it means that if you know one solution, you know another solution, and then you add these two solutions after multiplying by arbitrary constants, the result from the addition is still a solution to this equation. A very fundamental property that we use again and again later in the class. So that said, suppose that I pick two solutions that I already saw. One of them is a forward propagating wave, the other is a backward propagating wave. So here they are. The one with the minus is propagating forward, the one with the plus is propagating backward. So your colleague here asked, what will happen if I superimpose them? So one of them is going to the right, one is to the left. Are they going to cancel? What are they going to do? Okay, so this is computational, so perhaps you should not trust it. After all, what is this? But anyway, this is what I got in MATLAB when I simulated this. Okay, let me play this again. So this is the result of the two waves. Okay, I pushed the button, I did not play the movie again, I revealed the derivation, but that's quite all right. Okay. Okay, so I meant to do this on the freehand here. Okay, never mind, ignore what you see on the slide and just watch the whiteboard. I guess I can call it whiteboard, can't I? I mean, it is a whiteboard. Okay. Okay, so here are the two waves. So I actually omitted, I should have said that not only are they counter-propagated, but also I picked them both to be harmonic waves, so that we can do the math easily. Okay, so let's write this out. So we picked the exact, the identical amplitude. So one of them will be written as, did I use A or as A? Yeah, okay. Okay, now for generality, I don't really have to, but for generality, I also added a phase delay phi to the first wave. So this one is forward, and then I have the other one, which looks very similar, except for this devious minus sign. That goes backward. Okay, and the superposition principle says that I can simply add the two waves, and the summation is still a solution to the wave equation, therefore still a valid wave. Okay, so what is the result? So now, I don't know how to tell you to remember this. Most people look it up in books of trigonometry. I have a certain mnemonic for it, but I will not tell you. But anyway, so there's a mnemonic that says if you have the sum of two cosines equals, now this is a mathematical property, so there's no intuition to be derived here. This is just obtained by trigonometric manipulation, equals twice cosine a plus b over 2 cosine a minus b over 2. Okay. So I never remember this one. I will tell you actually my mnemonic is nothing strange. All I remember is that if you have cosine of a plus of two things, it equals let me write it clean on a clean piece. Okay. So cosine of two things it has a minus sign here, and sine of two things okay, these two I have memorized, and you can see very easily that from these two you can obtain the equation we said before, because for example you can write cosine alpha plus beta plus minus beta equals cosine alpha cosine beta minus plus sine alpha sine beta. Okay, so if you add the term with the plus and the term with the minus, the sine terms evaporate and you end up with the identity that they had before. So this is my mnemonic for remembering this one. We will not have to do this too often because last time, if you remember, we introduced phasors. We introduced a complex notation for waves so that we don't have to deal with this trigonometry very often. In this case, there's no way out because, well, actually there's a way out, but it is simpler to do it this way. Okay. Right, so now I have basically A equals kz minus omega t plus phi, B equals kz plus omega t plus phi. So if you apply my formula here, you will find that the wave actually, okay, the amplitude is the same, I pick up a factor of 2, so it is 2, and then I have the cosine of the sum, so if I sum the two, the time term will disappear, so we'll have cosine, and there is, well, you get twice of each, but there's a factor of 2 here, so they cancel, so it will be cosine kz plus phi. And if I subtract the two, then actually the spatial terms and the phase will disappear, and I will get a cosine omega t. Okay, now do I believe MATLAB? I think I should believe MATLAB because let's see what did MATLAB show. Here time is frozen, so you see basically the same term where this has been replaced by constant because I froze time. So indeed, this looks like a sinusoid of the same frequency as we had before. And actually, of course, you have no way of knowing that, but the waves that I entered had an amplitude that was half of this. So basically, the factor of 2 was also reproduced by my simulation. Okay, now if I play the movie again, it is basically like unfreeze in time. Okay, so here I have unfrozen time, and you see that I get a sinusoidal variation in the time domain. So therefore, that's my term cosine omega t here. So basically, the MATLAB simulation is correct. So we're very happy. Okay. So now let me come to your question. What happens to the wave when it vanishes, right? First of all, it doesn't really vanish, right? I don't know how to go back. Okay. So it does look like at some point the wave vanishes and then it reappears. Okay, it is a little bit annoying that it vanishes, but in electromagnetic waves and usually in other kinds of waves, we don't worry about the instantaneous energy, we worry about the average energy. So what you can see here is that the average energy is actually conserved because as the wave oscillates from a maximum to a minimum, its average energy remains the same. Now you might ask, well, what happens in between? I mean, you know, what happens when this wave has gone to 0? Again, I will answer the case of electromagnetic waves. What you have done here is you have basically launched two waves that are moving in opposite directions, right? So who is providing the energy? Well, you are providing the energy on one end, and someone else is providing the energy on the other end, right? So what happens when the two waves cancel is that the energy is actually stored in another place which does not show up in this equation. That's one way to think about it. So if you remember when I saw, actually you don't remember because you were not in the class 1 week ago, but I showed an example of a simple harmonic oscillator, right? So simple harmonic oscillator goes from 0 velocity maximum potential energy to the edge where the velocity now is, to the rest position where the velocity is maximum and the potential energy has become 0, right, at the rest position. So it's the same kind of thing. The kinetic energy disappears. Well, what happens to it? It has become potential, right? So it's very similar to this. The energy has become potential energy, and you don't see it here. Yeah.
Okay, maybe a follow-up on the question. So now let's assume the two waves are traveling along the same direction, and they are out of phase by pi. So in this case, they will perfect cancel each other.
Right.
So where does energy go? Just for your information, the previous answer I get is such thing will not happen in the first place, but I'm just not comfortable with this answer. So I would like to know your comments.
Well, if the two waves start at pi phase shift, it's equivalent to that not having launched any wave at all, right? Whoever launched the two waves basically cancelled his own action. So if you think about it physically, what happened, right? So, first of all, have the two waves been launched at infinity or at a finite time?
So for example, now I launch a wave at z equals 0, and this wave traveling to the to the positive direction and continuously. Now I launch another wave at z equals, for example, z equals -10, but this wave only lasts for 3 periods, for example. So as this wave traveling into a positive direction, it is going to cancel 3 periods of the previous wave, right?
Now you're making it a little bit more complicated, because what happens to the edges of the wave? Are you multiplying by a boxcar function? What happens later? Right? You're not given enough information to answer the question, right? You just tell me that 3 periods cancel, but then what happens later? Did you just stop the wave, or?
This part I'm still not so sure. Yeah, that's why I'll check. Yeah, thanks.
Okay.
Anyway.
The question is a bit ill-defined, I guess, so I cannot answer it. But I can tell you this. Suppose that I launch a wave at some time, and then a certain time later, I launch the same wave with pi phase shift, right? So there's no doubt that the two waves at this point will cancel. So what happened to the energy? Well, it is equivalent to thinking that I did not really launch a second wave with a pi phase shift, but I actually turned off the switch that was producing my first wave in the first place. Right? So there might be a transient or something like that, but in effect, I've just canceled the wave. So simply stopped the flow of energy. Right? I mean, that's an answer. Everybody happy with this answer, or should we discuss this? Okay. Another thing to realize, actually this is interesting that we brought up energy. In the standing wave, the energy is actually not going anywhere, right? Because you can, well, that's one way to think about it, it's not going anywhere. Or you can think about it in the way that the energy is going back and forth, right? So it's, yeah. Okay. So I just realized, actually, I did not do phasors last time, did I? Did I? I guess I didn't. Okay. Sorry. Okay. Right. So I guess I pulled the fast one. A few minutes ago, I was talking about the difficulty of trigonometry, and I said that's why I introduced phasors last time. I was mistaken. I had not introduced any phasors last time. I'm introducing phasors now. And the reason, of course, that we're introducing phasors is because we don't want to have to remember complicated identities like this one. Okay. By the way, another point that I would like to bring up before I move on to phasors is that the wave that I'm showing here is actually very different than the traveling wave that led us to the wave equation. You agree with that, right? That looks very different. Both in the way it behaves with time and space, and the way it looks like an equation. Yet it still originated from the same wave equation. So this is actually the power of partial differential equations and superposition, that I took two solutions of my partial differential equation that were not particularly interesting, I superimposed them, and then all of a sudden I created another solution, which is still a very valid wave, but behaves totally different. It is a stationary wave, it has this oscillation, and so on and so forth. So that is why we bother to write this partial differential equation, because it allows us to generate a much richer set of waves that are, of course, very important in practice. Standing waves happen all the time. Okay, so now let's go to phasors. Okay, so just like before I wrote two waves that were propagating in opposite directions, now what I'm going to do is I'm going to write two waves that are phase shifted by pi over 2. So one of them is cosine kz minus omega t plus phi, okay? And the other is phase shifted by pi over 2, which means instead of a cosine, it is a sine. Okay, both are valid solutions to the wave equation with different initial conditions, but that doesn't bother us, they're still valid solutions. Therefore, their superposition is also a solution. And I said before that when you do a linear superposition, you can also multiply the waves by arbitrary constants. I said this a little bit fast, but I hope that you remember that I said it. In fact, in this class, we have evidence of what I said and what I did not say. You can go back to the video and see if I said it, and I did. Okay, so I will pick a very particular constant, which may sound like a crazy choice, but I will pick it. And that's the imaginary constant I, also known as one of the two square roots of minus 1. Okay, what is this now? So the first confession that I will make is that it is not physical anymore. There's no such thing as a complex wave. The waves that we see around us are real. They can be measured by instruments such as oscilloscopes, cameras, I don't know what else. They're real. As far as I know, nobody has ever measured anything complex. However, what I'm doing here is mathematically correct, even if it has no physical meaning. And as it turns out, it provides a huge mathematical convenience. So I'm justified in doing it as long as I remember what is the physics that is behind it. And the physics that is behind it is that every time I see a wave like this, I have to remember that the physical quantity is the real part, okay? So the physical wave, the one that I can actually measure, observe, generate with, natural means, is the real part. Okay. The imaginary part is something that I added for mathematical convenience. And the reason I added it is because I forget whose formula it is, called de Moivre or the... Anyway, one of those... D-E-M... Moivre, yeah. De Moivre, yeah. Okay, I got it right. Okay. So de Moivre then, if I remember correctly, that's how you spell it. De Moivre says that this thing here is a complex exponential. Okay. So that's very nice because, for example, if you have to multiply two cosines, it's a big pain, right? You have to remember the trick. To multiply two exponentials, it is trivial. You just add their phases. I mean, their exponents. So a lot of convenience is to be expected. So this representation, it comes with different names, which are sometimes used confusingly in an interchangeable way. So some people call this a phasor notation. I prefer to call this the complex representation of the wave. It becomes a phasor when we drop, I'm going to do something nasty here. Okay, remember that I can write this as a product, right? So I can write this as e to the I k z, e to the minus I omega t, e to the I phi. Okay. If you recall, during the beginnings of the class, we saw that the wavelength in a medium changes. But there is a property of the wave that does not change. And that property, if you recall, is the temporal frequency, omega, or nu, which is related by 2 pi. Okay, that is true in linear media. Of course, there is a class of optics called nonlinear, where actually the frequency can change, it can double, or it can halve, or fancy things can happen to it. But in this class, we don't deal with these complicated things, we just deal with linear optics. So in linear optics, the temporal frequency of the light, no matter what happens to the light, even if it goes through glass and reflects and all kinds of things, the temporal frequency remains the same. So when we deal with optical waves of a single frequency, that is, the color is fixed and the medium is linear, then this term is actually superfluous. We don't have to remind ourselves that the light goes like e to the minus omega t. It does, but we don't have to write it, because if we keep writing it, it clutters our equations. So we simply drop it, okay? We drop it. Very important to remember, we are allowed to drop it if we know that we have a single color in our system, a single frequency. If there is multiple frequencies, we cannot do that anymore, right? Because then these frequencies have to adapt in a certain way, and we have to keep track of the relative phases. So we can only drop this term if we, two conditions, if we know that we have a linear medium and a single frequency light propagating in that medium. Okay, so in my terminology at least, after we drop this term, then it becomes a phasor. So what is left? E to the I k z plus phi, that I call a phasor. And you notice what happened there is I only left the spatial dependency of the wave plus the phase delay. The temporal variation it's hidden, it is not gone, it is just hidden. Okay? Okay, now let's see this in action. So what I'm going to do is I'm going to rederive the standing wave, but using the phasor, so you can see how nice and simple it comes out, and we don't have to agonize over it. But before I do it, I actually have to solve a little problem. And the problem is that I did this very nice derivation for the phasor of the forward propagating wave. What about the phasor for the backward propagating wave? Okay. The backward propagating wave would be something of this sort. So this all goes forward, right? Okay, now let me write the backward. I think I have enough space here so I can do it. Okay, so the backward would be something of the sort of the form cosine kz plus omega t plus phi. Now that is very inconvenient, because the way I got the phasor is I got rid of a term of the form e to the minus omega t. If I add the imaginary part here, I don't have a term e to the minus omega t, so I'm stuck. But I can do some mathematical trickery. Now this is pure trickery, but it works. The trickery is the following. We know that the cosine is an even function. So this is actually identical. I can replace it, in other words, with the cosine of the negative argument. No harm done. It is still a backward propagating wave. Nothing has changed. It is the same equation. Now, according to my good principle here, I add that is not the same as before, right? Because the sine is an odd function. But this is a non-physical term anyway. I just put it there for mathematical convenience, so I don't particularly care. I'm very happy because the real part is the same as I started with. What the imaginary part does, as long as it's mathematically convenient, I couldn't care less, right? Okay, so that gives me the license to write this. Now this, of course, equals e to the minus I kz minus I omega t minus phi. Now I'm very happy because I did get a term e to the minus I omega t in the phase of this exponential, and therefore I can drop it to produce my phasor. So the lesson then is that the phasor for the backward wave is e to the minus I kz minus I phi. In other words, if I give you a forward propagating wave and you compute its phasor, and then I ask you, well, what is the phasor for the backward propagating wave? Well, all you do is you flip the sign in the exponent. Okay. Fine, so now that we have this, can we produce, whoa, where did this come from? I think this is an old paper from some previous lecture. But anyway, ignore this. I have to remember to ask for a new paper next time. Okay, so what I will do now, let me reproduce the standing wave. So the standing wave is, using the phasors now, is e to the I kz plus phi, that is the forward wave, plus e to the minus I kz minus I phi. That is the backward wave. Can I deal with that? Well, yes, actually, because again, the Moivre says that if you add two exponentials of this form, notice they have the same phase within a minus sign. I will simply get twice cosine kz plus phi. So I got my thing here. Not quite though, because the standing wave, it had the cosine omega t term. What happened to this cosine omega t? Oh, come on. Okay. What happened to the cosine omega t? Well, remember, we neglected an e to the minus I omega t. We didn't really neglect it, we hid it, because we didn't want to carry it when we write the equations. Well, first of all, if I don't care about the temporal variation, I don't really have to do anything, I'm done. But if I want to put the temporal variation back in, what I have to do is I have to put back what I took when it did not belong to me. And what did not belong to me is this e to the minus I omega t. Okay, I put it back. Now that is still not a physical wave because it is complex. How can I find the actual physical wave? Well, I have to take its real part. And the real part is easy here because the only complex thing is this exponential. So if I take the real part of this, of all of this now, it would simply be 2 cosine kz plus phi cosine omega t, and I'm done. I've actually reproduced my standing wave. Any questions? We're almost done here, so I have about 3 minutes, so I think I will use them to finish up this lecture so we can move on to bigger and better things. The equation that I wrote before is the one-dimensional wave equation, because the waves that I've written, they can only go down one spatial axis, right, z. The more generalized, of course, situation is three-dimensional waves. And what you see here is the generalized three-dimensional wave equation, which of course I will not derive, but it can be pretty easily derived using the same arguments that we did before, except you have to kind of generalize them in 3 dimensions. And this produces things that we've seen before in geometrical optics. For example, a plane wave, except now you see the wave description. It is, you have alternating positive and negative how do you call those, peaks and troughs, which are propagating along an arbitrary angle. Now they can go in any angle in 3D space, right? this particular, so you see just see a cross section here, or you can have a spherical wave, which we saw it before. It starts at a given point and then radiates outwards. So that's a spherical wave. Well, we're not quite finished yet, but I think we're almost out of time. So I think I'll stop here and we can still continue next time. Are there any questions? There's no homework due on Wednesday, so what I would like to, you have a question or? Yeah, there's a question, go ahead.
How is the wave equation intuitively different from simple harmonic oscillator? Okay. Like the variation in space depends on the variation on time, so that's coupling.
Okay, yeah, the mathematical answer, of course, is very easy. The simple harmonic oscillator is an ordinary differential equation. This is a partial differential equation. But let me think how to formulate a physical answer. Okay, so the physical answer is that the harmonic oscillator is a single particle whose position you track as a function of time, right? A wave is a distributed physical system. So you can think of a wave, in this case, for example, you can interpret the physical meaning of these black and white stripes as particles which are moving. For example, the particle that is on the white stripe is moving up, the particle in the black stripe is moving down, right? So if I play the wave again, what you'll see that the particles are kind of executing a coordinated motion, right? Because you have particles that were down, then they go up, then they go down again, but they go out in a coordinated motion throughout the entire plane. How do they know? Well, there's a physical system associated with this. For example, this could be a membrane with the sound wave propagating on it, right? And now the reason the particles are connected, they execute the coordinated motion, is because of the interatomic, forces between the membrane particles. If it is an electromagnetic wave, then it is a field that is distributed, and of course it knows to be connected because of Maxwell's equations, right? There's things like charge conservation and so on that force it to act this way. So a wave is actually a distributed system where the physics force an extended systems, particles or fields or whatever the case may be, to execute a coordinated motion. That's the difference between the simple harmonic oscillator where you just have one particle. Now you can go from one to the other. Imagine you take a single harmonic oscillator. That's a good one. So let me draw it here. Wow, we're actually going backwards now in the notes that I used in the past. So you take a simple harmonic oscillator. Here it is, right? A pendulum. Right? This is a simple harmonic oscillator. Then you couple it with a second pendulum. And how do you couple? They're not coupled at the moment, but you can couple them, for example, by connecting a spring in between, right? Okay, that's not quite a wave, but you can see now that because I coupled them, if I kick one of these, it will also cause the other one to move, right? So they become coordinated. Well, now let me generalize. Imagine that I have a bunch of harmonic oscillators, and in fact I can make them infinite, and I couple them. Now, in fact, this system will become wave-like in the sense that if you kick it at one end, okay, let's say not at infinity, let's say it starts actually here, and then it goes to infinity. Right? So if you kick it at one end, then the disturbance will actually propagate very similar to a wave. It's a discrete wave, but it's still a wave. So you can go from one to the other by introducing a kind of a coordination mechanism. So it is the coupling here that does the coordination. Any other questions? We can stay here, actually. Nobody claims the classroom is either here or there. So if you have more questions, I'll be happy to stay and answer them. What about the phasors? Is it clear? The phasors, I realized the phasors, when I was your age, when I was a student, I was also very upset by phasors because they look very much like mathematical trickery. I mean, I'm trying to find my I guess that's one benefit of this over the whiteboard, that I have a history of what I did. But yeah, but the phasors, they look very much like mathematical trickery. I mean, it looks like someone pulled it out of a hat. But the only reason to justify it in your mind is that it provides huge mathematical convenience. Now this looks like a trivial thing. I mean, the derivation of the standing wave was maybe 4 lines with trigonometry, 2 lines with the complex exponential. So, okay, why mess with complex numbers? Well, try superposition. If we have like, you know, several waves superimposed, or if we have an integral, a continuum of superimposed waves, which we'll see very soon, like Fourier transforms and so on, Fourier transforms are extremely inconvenient if you write them as cosine transforms. Big mess. If you write them as complex exponentials, it's actually very simple to do the math. So it is a very time-saving tool, basically. And also, strangely enough, it leads to some insights that the real numbers do not give you. So that's an additional convenience. But I mean, we will appreciate that later. For now, it is simply the mathematical convenience that drives this mathematical wizardry, if you wish. Yeah.
Yeah. Is there any instant when the angular frequency and the temporal frequency are different, or it's the same? Because you initially defined omega as angular frequency.
I confuse those myself usually, the terms. Usually nu is called the frequency, and it is measured in hertz. 2 pi nu is measured in radians per second, and is defined, what's the point? Angular frequency, isn't it? Yeah. Oh, as opposed to what else? I guess I don't understand the question. Yeah, what I mean is that for example, take the propagating wave. The propagating wave is e to the I, let's say forward, right? Kz minus omega t. The standing wave is cosine kz e to the minus I omega t. I'll step ahead a little bit and write something awful. Okay. This is actually a wave. It is what we'll see later is called a diffraction integral. And you can see it is nothing, even though it looks really complicated, it is just a superposition, right? Because the integral is a summation, and then what I have here is a phasor, and I put a lot of these phasors together. What they all share is this term e to the I minus I omega t. Okay. So I could actually, to be strictly correct, I should really carry this term. I'm not really allowed to drop it. But because it is the same always, I might just as well not write it. No, so it basically saves me writing. And also confusion, because as you know, the more things you write, the more likely you are to make mistakes, right? So it is typical in these derivations, if you don't need something, you drop it, right? Because if you start carrying it around, it invokes mistakes. So that's why I would drop this term. Right? So I can just as well say that if I have a propagating wave, I can just write it as e to the I kz. That's a propagating wave. I have a standing wave, I can just as well write it cosine kz. Okay, the e to the minus I omega t is implicit, right? If I have this diffraction integral, I can just write it without this term. But again, the term is implicit. If I have to figure out what is the temporal variation of the wave, I have to put it back in. And again, I cannot do it if I have two waves of different frequencies. If I have e to the I omega, let me write another superposition. E to the I k1z minus omega 1t plus e to the I k2z minus omega 2t. That's still a valid superposition, right? Provided that the ratios of these, k1 over omega 1 equals c, k2 over omega 2 equals c, still a valid superposition. I'm not violating anything. But I cannot do the phasor trick anymore, right? I have to keep the e to the I omega t terms, or I will make a mistake. There's one more case when if you produce any kind of nonlinearity. We will see later. And again, we're going a little bit ahead. I'm in trouble here. These are from the quiz. Okay, we'll see a little bit later. When we try to compute the flux of electromagnetic energy, there's something called the Poynting vector, which is defined as the electric field cross with the magnetic field. Okay, if you try to write the expression for the Poynting vector, you cannot just multiply the phasors of the electric and the magnetic field because it's a product. So you can use phasors only when you have linear operations, such as additions, right? Or integrals. In this case, you can't. We will see what you do in this case. You do a temporal average, but there's a few cases where one has to be careful with these phasors.